Hello students. So today we'll continue a chapter that is NCERT chapter 7 Alcohol, Phenols and Ethers. And today is a theory part 6. So this is the disclaimer. Now what is the objective of today's lecture? So after attending this lecture, you'll be able to understand the topic which we are going to cover today. So today we are going to correlate the physical properties of alcohol, phenols and ethers with their structures. Now for your reference, I have mapped the NCERT sections that I am going to cover today. So the sections which I'll be covering is 7.4.3, that is physical properties of alcohols and phenols. And we will solve an example, that is 7.3. We'll solve one NCERT example question, that is question number 1. And we will solve NCERT exemplar multiple select question, that is question number 17. And then at last, we will solve an NCERT exercise question, that is 7.33. Okay, so let's begin with today's lecture. So first we are going to see the physical properties of alcohols, phenols and ethers. So we will compare the boiling points, that whose boiling point is more and whose boiling point is less, and what is the reason behind their boiling points. So first, if we see the boiling points of alcohols and phenols. Now we know that in alcohols and phenols, we have OH group, that is the hydroxyl group. Now because of this OH group which is present, there is strong intermolecular hydrogen bonding. Okay, so there is intermolecular hydrogen bonding. So if the bonding is strong, so that means you have to require more energy to separate the molecules. Imagine a situation where a group of students are standing and they are tightly holding their hands. So if they are tightly holding their hands, it would be difficult for you to separate them. Or you have to apply more energy to separate them. Similar is the case in alcohols and phenols. Because the intermolecular hydrogen bonding is strong. So if the bonding is strong, you have to give more energy to separate the molecules. So if you have to give more energy, that means the boiling point of alcohols and phenols will be higher as compared to ethers and hydrocarbons. Boiling point means that when you have to boil any substance, first you have to bring the temperature to its boiling point. Okay, after increasing the temperature to its boiling point, then it changes into the gas phase. So the important thing is first you have to raise the temperature to its boiling point. So that is the case of alcohols and phenols, that there is the boiling point is higher if we compare it to ethers and hydrocarbons. Now look at this picture. In this picture, there is intermolecular hydrogen bonding. First you can see is of phenols and other one you can see is of alcohols. So I hope you are clear with intermolecular and intramolecular. Intermolecular is when it is between the two different molecules. Okay, means between two molecules. And intra is when there is hydrogen bonding between the same molecule. So here we are seeing intermolecular, that is between the two molecules. Okay, first C of alcohols. So this is an alcohol group, that is ROH. A hydroxyl group is attached to this carbon atom. And similarly, you can see this is also an alcohol group. That is, the hydroxyl group is attached to your R group, that is any alkyl group. Now you know that oxygen is more electronegative than hydrogen. So look first towards this molecule of alcohol. Here you have oxygen, here you have hydrogen. So oxygen being more electronegative than hydrogen will take the shared pair of electrons from the hydrogen. So a partial negative charge will be developed on oxygen and a partial positive charge will be developed on hydrogen. Similarly, look at this another molecule of alcohol. Same is the case. Oxygen is more electronegative, so it will withdraw the electron density from the hydrogen. So this oxygen will develop a partial negative charge and this hydrogen will develop a partial positive charge. Now look at the cursor on the screen. This oxygen has a partial negative charge and this hydrogen has a partial positive charge. So the charges are different. When the charges are different, they attract each other. So this oxygen will take the electron density from this hydrogen. That is this oxygen and hydrogen bond which you can see. This is the hydrogen bonding. Because this oxygen is negative charged, has a partial negative charge, and this hydrogen has a partial positive charge. So this oxygen will withdraw the electron density from this hydrogen. Okay, so this which you can see with the red dotted lines, this red dotted line shows you the hydrogen bonding. Intermolecular hydrogen bonding. Intermolecular, why? Because it is between two alcohol molecules. So this is hydrogen bonding. Similarly, you can see towards this oxygen, if there will be one more alcohol group, so this will also show hydrogen bonding. So in case of phenols, in case of alcohols, this intermolecular hydrogen bonding is strong. Okay. Now look at the case of this phenol. In phenol also, since there is hydroxyl group, so you will see the hydrogen bonding in phenol also. Okay, because phenol also has your hydroxyl group. Now if I talk about ethers, I hope you remember the structure of ethers. In ethers, what is there? There is oxygen in between, and to the oxygen, the right and the left side has alkyl or aryl groups. So this is how ether looks like. Now the alkyl or aryl group can be same on both the sides. That is, it can be methyl on both the sides, or it could be different. Like on one side there could be methyl and on other side there could be ethyl. So this is structure of ethers. So in ethers they have carbon oxygen single bond. Okay. So if there is carbon oxygen single bond, again there will be polarity between carbon oxygen single bond. Okay. So oxygen being more electronegative will withdraw the electron density from the carbon. So oxygen will have a partial negative charge and carbon will have a partial positive charge. So the CO bond in ether is polar. Okay, so there are dipole-dipole interactions which is present. So in ethers, there is no hydrogen bonding because you don't have hydroxyl group present in ether. But you have CO single bond present in ether, which is a polar in nature. So because of that CO bond, there is dipole-dipole interactions. But these dipole-dipole interactions are weaker than strong hydrogen bonding. Okay, so since these dipole-dipole are weaker than strong hydrogen bonding, so you have to provide less energy for the molecules to get separated, means to get boiled. So the boiling point in the case of ether, it is higher than the hydrocarbons, but it is lower than alcohols and phenols. So boiling point of ether is less than alcohols and phenols because the dipole-dipole interactions are weaker than the hydrogen bonding. So you have to provide less energy for the molecules to separate and hence the boiling point will be less. But if we talk about hydrocarbons, then in hydrocarbons there is only weak van der Waals force is present. Okay, now since this van der Waals force is weak, so that means in hydrocarbons you have to give more less energy for the molecules to separate. So if you are giving less energy, that means the boiling point will be lower as compared to alcohol, phenols and ethers. So hydrocarbons has the lowest boiling point. Okay, so here we compare the boiling points of your alcohol, phenols, ethers and hydrocarbons. Okay, but in the case of phenols, if you see, in phenols you have this benzene ring. Okay, So because of this benzene ring, if I say, then phenols have lower boiling point as compared to alcohols. If I compare alcohols and phenols, because of this benzene ring which is present over here. Okay, so if I compare the order of boiling points, then your alcohols and phenols has the highest boiling point, then comes the ether, and then comes the hydrocarbons. So the simple reason, if I have to sum up, I will say that in alcohols and phenols there is strong intermolecular hydrogen bonding, so you have to provide more energy for the molecules to separate, so the boiling point is more. Whereas in ethers, there is dipole-dipole interactions because of the polar nature of CO bond. So in ethers, you have to provide less energy because dipole-dipole interactions, they are weaker as compared to the hydrogen bonding. So if you have to provide less energy, that means the boiling point will be less. Now, if I talk about hydrocarbons, then in hydrocarbons, you know that there is weak van der Waals forces. So if the van der Waals forces are weak, that means it will have a lower boiling point compared to alcohols, phenols and ethers. So this is the order of boiling point. Now let's move forward. Now we will see the factors that are affecting the boiling point in alcohols. So first factor that we will see is the molar mass. Okay. So the trend is that the boiling point increases with the increase in molar mass. So if the molar mass is increasing, you will see that your boiling point will also increase. Okay, this is because of the van der Waals force increases. So what happens is that when your molar mass is increasing, so your electron cloud becomes more big. So if the electron cloud becomes more big, it will be easily distorted. So it will create a stronger dipole. It will create a stronger temporary dipole, and your van der Waals forces will be strong. So if the van der Waals forces are strong or the van der Waals force increases, then you have to provide more energy for the molecules to separate. So if you are providing more energy, then the boiling point will be more. So you need to remember that the boiling point will increase with the increase in the molar mass. Okay, now look at this example. There are 4 molecules given to you. First is methanol, ethanol, propanol, butanol. Now, see, butanol has 4 carbon atoms, propanol has 3 carbon atoms, ethanol has 2 carbon atoms, whereas methanol only has 1 carbon atom. Now I told you, increase in molar mass increases the boiling point. So butanol will have the highest molar mass. Propanol will come after butanol, then ethanol, and least is methanol. So since butanol has the highest molar mass in these 4, so the boiling point of the butanol will be higher. Then it comes propanol, then methanol, then comes the propanol, ethanol, and then methanol. So this is the trend. Okay, butanol, propanol, ethanol, and methanol. So if different compounds are given to you and it is asked about the boiling point, then you can calculate their molar mass, and which one will have the highest molar mass, their boiling point will be most. Next is the branching. So molar mass is one of the factor that affects your boiling points. The next factor comes the branching. So boiling point decreases with increase in branching. Now, if the branching in your compound is increasing, you will see that there will be decrease in the boiling point. Okay, this is because now if there will be more branching, consider if there is a straight carbon chain. So if the carbon chain is straight, you will see the surface area will be more. But if there will be branching in that carbon chain, you will see that the surface area will be less. So if the surface area will be less, then the van der Waals force will decrease. Okay, so if the van der Waals force is decreasing, means the boiling point will be less, because you have to provide less energy for the molecules to separate out. Okay, so look at this example. you have butane 1-ol. I hope you all remember how we do the IUPAC nomenclature. In this carbon, there are 4 carbon atoms. And to the first position, your hydroxyl group is attached. So it is butane 1-ol. Okay. Now, look at this. That is butane 2-ol. So, if you will see this, then see 1, 2, 3, 4. 4 carbon atoms. And on second position, you have a hydroxyl group. So, this is butane 2-ol. Okay. And now look at this carbon. In this carbon, at your second position, there is a methyl group as well as there is an OH group. So, it is 2-methyl propane 2-ol. Now, look at this carbon. This is a tertiary carbon because this carbon is further attached to 3 carbons. And this carbon is a secondary carbon because this carbon is further attached to 2 carbons. Okay, now let's come what I was telling, that the boiling point decreases with increase in branching. So that means in 2-methyl propane 2-ol, it has the most branching. So since this methyl 2-propanol has the most branching, then the surface area will decrease. If the surface area will decrease, that means the van der Waals force will also decrease. Okay, that means your butane 1-ol will have the highest boiling point, then comes the butane 2-ol, and 2-methyl propane 2-ol will have the least boiling point. Why? Because it has a branching. This compound has branching. So if this has branching, the surface area is less, so your van der Waals force is also less. Van der Waals decreases, so you have to provide less energy. Okay, so butane 1-ol will have the highest boiling point because it is a straight carbon change. So there are the 2 factors, that is the molar mass and the branching. So your boiling point increases if the molar mass increases, and your boiling point decreases with the increase in branching. Because when branching increases, the surface area and van der Waals force decreases. Okay? Okay. Now let us see the solubility in water. How alcohol phenols, is it more soluble in water or is it less soluble in water? Now we will see that the lower molecular mass alcohols are soluble in water. Lower molecular mass alcohols means which has less number of carbon atoms. If they will have less number of carbon atoms, then their molecular mass will also be lower. So if the molecular mass is lower, then they are more soluble in water. The reason is because of the formation of hydrogen bonds with water molecules. Now your alcohols and phenols also have the hydroxyl group, and your water molecules also have the hydroxyl group, that is the OH group. So hydrogen bond is present between your alcohols, phenols and water molecules. So, and one more factor is that your solubility will decrease as the non-polar alkyl or aryl group size increases. Now when you will move to higher molecular mass alcohols, that will have more number of carbon atoms, so you will see this alkyl or aryl group will increase. Now this alkyl or aryl group is non-polar. Non-polar because they don't have any carbon oxygen bond. Okay, so this alkyl or aryl group is non-polar. So if this group will increase, then your solubility will be decreasing. So you have to remember this. So hydrogen bond is disrupted by the large alkyl or aryl group. So as I told you, this alkyl or aryl group, these are non-polar groups. So if they are non-polar, then they will affect your hydrogen bonding. Or we will say that my hydrogen bond formation will be disrupted. So if it will be disrupted, so it will be less soluble with water. So if you see this, it is a propanol molecule is given to you. This is CH3, CH2, CH2OH. So this is a propanol molecule which is given to you. And in propanol molecule, it is told that this is a hydrogen bonding between propanol and water molecule. Now this red dots which you can see, this shows the hydrogen bonding. Now you all know that oxygen and hydrogen bond is polar bond. Because oxygen is more electronegative, so it will withdraw the electron density from this hydrogen, and it will acquire a partial negative charge, and hydrogen will acquire a partial positive charge. So look at this. This oxygen is bonded to two water molecules, that is the hydrogen of the water molecules. So oxygen is withdrawing electron density from this hydrogen atoms. Okay, so this is the hydrogen bond between oxygen and hydrogen. And similarly, look here, this is the H of your propanol, and this is the oxygen of your water molecule. So since oxygen being more electronegative is withdrawing the electron density from this hydrogen. So this is red dots represent the hydrogen bonds. So this oxygen will develop a partial negative charge and this hydrogen will develop a partial positive charge. And see, in this case of propanol, this is a small carbon chain. There is only 3 carbon atoms. So because this alkyl group is small, so propanol is soluble in water. Now when this alkyl group will keep on increasing, your hydrogen bond formation will be disrupted because this alkyl group is non-polar in nature. Okay, so because of its non-polarity, your solubility will decrease. So only the lower molecular mass alcohols are more soluble in water. If you will increase the alkyl or aryl chain, then you will see the hydrogen bond will be disrupted and your solubility will decrease. And if I talk about phenols, then phenols are sparingly soluble in water. Okay, because what happens that in phenols, the ability to form the hydrogen bonds with water is counteracted by the large non-polar benzene ring. Now we know that in phenols also the hydroxyl group is present. So that hydroxyl group will form the hydrogen bond with water molecule. But what happens in phenols? In phenols, you have a benzene ring, and that benzene ring is non-polar in nature because the benzene ring is made up of carbon atoms. So there is no polarity between the benzene ring. So the benzene ring is non-polar in nature. So your ability to form the hydrogen bonds is counteracted by this non-polar benzene ring. So these are sparingly soluble in water. Okay, and lower molecular mass alcohols are more soluble in water. So I hope this solubility in water point is clear to you. Okay students, so now whatever I've taught you, we will solve some questions. So it will help you to understand more. So the question is saying, arrange the following sets of compounds in order of their increasing boiling points. So set A and set B is given to you. You have to arrange in order of the increasing boiling point. So set A is pentane 1 all, butane 1 all, butane 2 all, ethanol, propane 1 all and methanol. And set B is pentane 1 all, N-butane, pentanol and ethoxyethane. Okay, so I am giving you some time. Solve this question and then we will discuss the solution. So you have 40 seconds with you and your time starts now. Okay, so let's see the solution. So we right now studied that what are the factors that affect your boiling point of alcohols. So we saw that your carbon chain length affects the van der Waals forces. Okay, that if the molecular mass will be more, then your van der Waals force is more, and then your boiling point will also be more if your molecular mass is more. Next is the position of OH group. It affects the hydrogen bonding effectiveness. So the position at which your OH group is located in your compound, it affects your hydrogen bonding. Okay, so let us see the structural information of the given compounds. So first, let us see for the methanol. So methanol means there is only one carbon atom, and to that carbon atom your OH group is attached. So the OH group is attached to first carbon atom in case of methanol. Now see ethanol. In ethanol there is two carbon atoms. So there are two carbon atoms in ethanol, and to this carbon atom, look at the screen, to this carbon atom your OH group is attached. So two carbon atoms with OH attached on first carbon. Next is propane 1-ol. Propane means three carbon atoms are there in the chain. So look, 1, 2, 3. Three carbon atoms are there, and to your first carbon your OH group is attached. So OH group is attached on first carbon in propane 1-ol. Next, we will see butane 2-ol. Butane means four carbon atoms. So 1, 2, 3, 4. And it is saying 2-ol. So 2 here is indicating the position of your OH group. So here your OH group is attached to the second carbon. I'll do the numbering from this side. 1, 2, 3, 4. So 4 carbons with OH group attached on second carbon. Next is butane 1-ol. Butane 1-ol means 4 carbon atoms, and 1-ol means your carbon, the OH group is attached to the first carbon. So 4 carbons with OH group on the first carbon. Pentane 1-ol. Pentane 1-ol means there are 1, 2, 3, 4, 5 carbon atoms, and 1-ol is showing that the carbon to which your OH group is attached is the first carbon. So 5 carbons with OH on the first carbon. So this is the structural information which is given to us from the compounds which we have seen. Now let us continue the solution. So you know that if there are more carbons, then there is stronger van der Waals forces. So if the van der Waals force is more, you have to provide more energy for the molecules to separate. So if energy is more, the boiling point will be higher. So for same carbon number, you have to also compare the OH position, that to which carbon your hydroxyl group is attached. The terminal OH allows better hydrogen bonding, because if there will be terminal OH group attached to your molecule, then this terminal OH will allow better hydrogen bonding as compared to the middle hydroxyl group. So let us see the order of boiling point. First comes the pentane 1-ol, because in pentanes there are 5 carbon atoms. So it will have since there are more carbon atoms, so the molecular mass is more, so the boiling point will also be more. Then comes the butane 1-ol. In butane 1-ol there are 4 carbon atoms, and your OH group is attached to first carbon atom. After this comes the butane 2-ol. In butane 2-ol, the OH group is attached to your second carbon. So in this, since the OH is attached to the middle carbon, so I told that terminal OH allows better hydrogen bonding. So butane 1-ol will have more hydrogen, it will have higher boiling point as compared to butane 2-ol. Then comes the propane 1-ol. In propane 1-ol, I have only 3 carbon atoms, and your OH group is attached to first carbon. Then comes the ethanol, which has only 2 carbon atoms, and then comes the methanol. So this is the order of the boiling point. First highest is pentane 1-ol will have the highest boiling point, and methanol will have the lowest boiling point. So this is the solution of your A part. Now let us solve the B part. In B part, first we will decode the structures of the given compounds. So first is pentane 1-ol. First, let us see about N-butane. So butane 1, 2, 3, 4. 4 carbon atoms are there. So since there are 4 carbon atoms and your N over here is depicting that it is a straight carbon chain. So in this, there is only van der Waals force. There is no hydroxyl group present, so there is no hydrogen bonding here. Here there is only van der Waals forces present here. Now comes the ethoxyethane. In ethoxyethane, there is van der Waals forces plus there is weak dipole-dipole interaction because there is carbon-oxygen bond. Okay, so this is ethoxyethane. So in this, there is van der Waals force plus weak dipole-dipole. Now, if I say about pentanol, then in pentanol, a aldehyde group is present. So there is van der Waals force and dipole-dipole interaction because there is carbon double bond oxygen present in pentanol. So there will be bond polarity here. Next is pentane 1-ol. It is an alcohol. So in alcohol, the hydroxyl group is present, OH group. So there will be van der Waals forces also, and there will be strong hydrogen bonding also. So one by one we decode it. It is butane. So there is only van der Waals force. It is ethoxyethane, which is an ether. So it will be van der Waals forces and weak dipole-dipole because of carbon-oxygen bond. Single bond, carbon-oxygen, single bond. In pentanol, it is an aldehyde. So there is carbon-oxygen double bond. So there is van der Waals force and dipole-dipole interaction will be strong in this case as compared to ether one. And then I have alcohol, and in alcohol, you know, there is strong hydrogen bonding. So therefore, the correct boiling point is first comes the pentane 1-ol, because in pentane 1-ol it is an alcohol. So alcohol has the strongest hydrogen bonding. So you have to give more energy for the molecules to separate. So the boiling point will be more. Then comes our aldehyde group, that is pentanol. So in this there is van der Waals forces and dipole-dipole interaction because of C double bond O. That is the bond polarity is there. Then comes the ether, that is ethoxyethane. In ether, we know that there is van der Waals and there is weak dipole-dipole interaction. And then comes the simple alkyl group, that is N-butane, in which there is only van der Waals force. Remember, I told in first slide that your alcohols has the highest boiling point. Okay, then here comes the ethers, and at last comes your hydrocarbons. So this is the correct order. So whenever such questions are given to you, first decode its structure. Once you decode the structure, then you can write the correct order of the boiling point. Okay, now let us move to the next question. It is an NCERT exemplar multiple select question number 17. So the question is saying that which of the following are used to convert RCHO into RCH2OH. So this is an aldehyde group and this is an alcohol group. So aldehyde group is reducing into the alcohol groups. So remember where I taught you that how you can reduce your aldehyde groups to the alcohol groups. What reagents you will use. So 4 options are given to you, and remember it is a multiple select questions. Okay. So first option is H2PD. Next is LiLH4. C is NaBH4 and D is reaction with RMGX followed by hydrolysis. So this is a Grignard reagent which is followed by hydrolysis. That means you are breaking the compound in presence of water. So solve this question. I am giving you 30 seconds and then we will discuss the solution. Okay, now let's see the solution. So the correct options are A, B and C. That your A, B and C will reduce your aldehyde group to your alcohol group. Now first option is H2PD. So remember while doing the alcohol, I told you about the catalytic hydrogenation. Okay, in catalytic hydrogenation, your molecular hydrogen H2 reduces aldehyde to primary alcohol in presence of a metal catalyst. And that catalyst can be palladium, platinum or nickel. Now look at the question. This is a primary alcohol. Okay, so in case of catalytic hydrogen, your molecular hydrogen reduces it to primary alcohol in presence of a metal catalyst. Okay, the reaction is, this is an aldehyde group, and in using H2 and a catalyst, see, it is reduced to primary alcohol. How primary? Because this carbon to which your OH group is attached is further connected by one carbon atom only. There is only one R group, so there is one carbon atom. So this is a primary alcohol. Next is LiLH4. So LiLH4 is a very strong reducing agent. So it is being a strong reducing agent, it will effectively reduce your aldehyde to your primary alcohol. Okay, the reaction is, this is an aldehyde. By using a strong reducing agent, you will see it will reduce your aldehyde to primary alcohol. Okay, now LiLH4 is such a strong reducing agent that it can reduce your carboxylic group also to alcohols. Okay, next is, let's continue the solution. Next is your NaBH4. Now NaBH4, that is sodium borohydride, it selectively reduces your aldehyde to primary alcohol. Now remember, I told you that sodium borohydride is a mild reducing agent, whereas LiLH4 is a very strong reducing agent. So being a mild reducing agent, it will reduce your aldehyde to primary alcohol. Everywhere see, it is primary alcohol. So the reaction is, this is your aldehyde. Using sodium borohydride, you have reduced it to your primary alcohol. That is, the carbon to which your OH group is attached is further connected only by one carbon atom. Now last option is RMGX. There is Grignard reagent, and this is not the right option, because what happens in Grignard reagents, it adds the R group to the aldehyde. So if there is aldehyde, look here, this is aldehyde. So one, the R group is already present. Next, it will add the R dash group, that can be alkyl or aryl group, to this carbon. So that means this carbon over here becomes your secondary carbon. But in question it is asked only primary alcohol is asked. Okay, so in this case of Grignard reagent, look at this thing. You will see that to this carbon your R group will also attach. So this carbon will become a secondary alcohol. Why? Because this carbon is further connected to two other carbons. But in this case, we need only a primary alcohol. So that is why your Grignard reagent, which is followed by hydrolysis, is not the right option. Because you can see at this carbon, your R dash group will also attach. So this becomes a secondary alcohol. So that is why this option is incorrect option. So only your sodium borohydride, catalytic hydrogenation, and lithium aluminum hydride will be your correct option for this question. Okay, don't get confused, your RMGX will also reduce your aldehyde to alcohol, but it will form a secondary alcohol, not a primary alcohol, and here we need a primary alcohol. That is why your option D is incorrect. Okay, students, so let's move to the next question, that is NCERT exemplar question 1. It is saying that monochlorination of toluene in sunlight, which is followed by the hydrolysis with aqueous NaOH, yields. So you have to first see a toluene, and there is monochlorination of toluene in sunlight, and this is the first step. And in next step there is hydrolysis with aqueous NaOH. So 4 options are given: orthocresol, metacresol, 2,4, dihydroxytoluene, and D is benzyl alcohol. So you have to select the 4 options. Out of this, one will be correct. So you have to write the reaction and then you have to solve it. So I'm giving you 30 seconds. You try and then we are going to discuss the solution. Okay, students, so let's see the solution. So the correct option for this is D, that is benzyl alcohol. So whenever there is monochlorination of toluene in sunlight, it gives you benzyl chloride. So if you are taking, there is a benzene ring to which a chlorine is attached. So there is monochlorination of toluene, it will give you benzyl chloride. Okay, and there is no chlorination that occurs at ring. So you need to remember that the chlorination is not occurring at the ring. So what will happen? This is the first step. On next step, there is hydrolysis with aqueous NaOH. So when the hydrolysis will happen, your benzyl chloride will give benzyl alcohol. That means it will undergo a nucleophilic substitution reaction to give benzyl alcohol. Okay.
So now let's solve the next question, that is NCERT exemplar question 1. So the question says that monochlorination of toluene in sunlight followed by hydrolysis with aqueous NaOH yields. So four options are given to you: orthocresol, metacresol, 2,4 dihydroxytoluene and benzyl alcohol. So you have to first write the reaction. So this reaction is taking place in two steps. Okay. So first you will write a reaction and then look at the four options. So I'm giving you some time to solve this question and then I'm going to discuss the solution. So you have 30 seconds. Your time starts now. Okay, students. So let's see the solution of this particular question. So first, the right option for this question will be D, that is benzyl alcohol. Now let us see that how this answers come. So whenever you're talking about monochlorination of toluene, so you all know the structure of toluene, that on a benzene ring a CH3 group is attached. So whenever we talk about monochlorination of toluene, when the reaction is done in the presence of sunlight, it gives us benzyl chloride. Okay, that means your chlorination is not occurring at the ring. This is an important point to note, that the chlorination is not there at the ring. And whenever this process follows, this goes away by a pathway, that is free radical pathway. So first, from toluene, when it reacts with sunlight, that is the monochlorination of toluene in sunlight, it will give you benzyl chloride. And then on the next step, the hydrolysis will happen with aqueous NaOH. And then your benzyl chloride, it will undergo the nucleophilic substitution and it will give you benzyl alcohol. So first you will get benzyl chloride and then you will get benzyl alcohol. Now look at this. This is the reaction pathway. So this is a toluene, that is a methyl group is attached to your benzene ring. Now the chlorination, that is the monochlorination of toluene will happen, and see here sunlight. That means in presence of light. So it will follow the free radical pathway and H will leave from here. So this H, one of the hydrogen will leave and you will see chlorine gets attached. So this is benzyl chloride. Okay, and see the chlorination is not occurring at the ring. So this is benzyl chloride that is formed. Now once this benzyl chloride will form, then we will have nucleophilic substitution reaction. Now see, this chlorine will leave away. Now when this chlorine will leave away, it will take the electrons of this carbon. So now this carbon becomes electron deficient. Okay. And we know that aqueous NaOH, it gives Na plus and OH minus. So what will happen? Your Na plus and Cl minus will leave from here. So NaCl will leave. Now you can see that this carbon is electron deficient carbon. Now who will act as a nucleophile here? This OH, because this oxygen has lone pairs to give. So this oxygen will give it lone pairs to this electron deficient carbon and this will be a nucleophilic substitution reaction because this is a nucleophile and this carbon is acting as an electrophile. So OH will come to this position and it will form a benzyl alcohol. So you can see it is benzyl alcohol. So the final product is benzyl alcohol. Therefore, the option D is correct. Now let us move to the next question. In next question, it is saying it is NCERT exercise question 7.33. Now see, this question is saying when 3-methyl butane 2-ol is treated with HBr, that is hydrogen bromide, the following reaction takes place. So see, this is 3-methyl butane 2-ol, and when this is reacting with HBr, you can see this reaction is taking place, that this compound is forming. So you have to give a mechanism for this reaction. Reactant is given, product is given. So you can see in product what is happening. This OH group is leaving and this Br gets attached to this position. So you have to give the mechanism for this reaction, and to solve this question a hint is given to you. The hint is that the secondary carbocation formed in step 2 rearranges to form a stable tertiary carbocation by a hydride ion shift from third carbon atom. So use this hint and solve this question. Okay. So I'm giving you some time. Take 30 seconds. Solve this and then we will discuss. Okay, students. So let's see the solution. So what is happening? In this particular reaction, hydrobromination of 3-methyl butane 2-ol. So you can see initially our reactant was 3-methyl butane 2-ol. So hydrobromination is happening and this 3-methyl butane 2-ol is yielding 2-bromo 2-methyl butane. Okay. So this was our initial reactant, that is 3-methyl butane 2-ol. At third carbon, your methyl group is attached, and on second carbon, your OH group is attached. And hydrobromination is happening, and you can see that at second carbon, your bromine is getting attached. Okay, and methyl is also getting attached to secondary carbon to this carbon, to this second carbon, because naming is from 1, 2, 3, 4. Okay, so hydrobromination is happening. Now we will see the mechanism of this reaction. So the above mentioned reaction, it occurs in 3 steps. Okay. The first step is protonation of 3-methyl butane 2-ol, which is followed by the loss of water. This gives us a secondary carbocation. So look at this reaction. You have 3-methyl butane 2-ol. So first there is protonation. Okay, so protonation, this what happens in protonation, that this OH water becomes OH2 plus because protonation is happening. Okay, so after the protonation, you will see that here it is OH2 plus. Now oxygen is having this positive charge. So oxygen doesn't like the positive charge on itself. So what will happen? This group will leave from here and this carbon will now get a positive charge because see, here carbon is forming only 1, 2 and 3. 3 bonds are only forming. So this carbon will have a positive charge. So protonation is happening, and after that protonation this OH2 group will leave from here. Okay, that is the loss of water, and this gives us a secondary carbocation. So this, because this carbon is further attached to 2 carbons. So this is a secondary carbocation. Okay, but this secondary carbocation over here is less stable. So now we have to make it more stable. So let's see what we will do in further steps. Now what will happen? Since our secondary carbocation is less stable, so it will rearrange by 1,2 hydride shift to form a more stable tertiary carbocation. Now look at this picture. I told you here this carbocation is less stable over here. Okay, so if this is less stable, then 1, 2 hydride shift will happen and this will form a tertiary carbocation. Now see, this is a tertiary carbocation. Why? Because this carbon is further attached to three other carbons. That is, this carbon is attached to three carbon atoms. So if you see this secondary one and this tertiary one, so which is more stable, the tertiary one is more stable. See the alpha hydrogen of this carbon, 3 3 2, that is 3 4 5 6 7 8. 8 alpha hydrogen this carbon is having. So this tertiary carbocation is more stable. So to make this more stable, 1,2 hydride shift will happen and we will get a more stable carbocation. Now what will happen in the last step? Bromine here acts as a nucleophile. Okay, so bromine will act as a nucleophile. So nucleophilic attack will happen on this carbocation and you will get your desired product. So now see, you were having this 3-degree carbocation. Now here, this carbon is electron deficient. That is, it is acting as a carbocation. Okay, this is a carbocation which is electron deficient. So it will act as an electrophile. And Br minus, that is bromine, will act as a nucleophile. So this nucleophile will attack on this electrophile and you will see bromine get attached to this position. So you will get 2-bromo 2-methyl butane. So this was the three-step mechanism. In first there was protonation, which was followed by the loss of water molecule. In step 2, the second degree carbocation is less stable. So 1 comma 2 hydride shift will happen to make it more stable. And then there is nucleophilic attack by Br minus and you will get your desired product. Okay, I hope this is clear. So now let us summarize whatever we studied. We studied about the boiling points, that the order of this boiling point, that alcohols and phenols have the higher boiling point, then ethers, and then comes the hydrocarbons. Because your alcohols and phenols, it has strong intermolecular hydrogen bonding. So stronger will be the bonding, then you have to give it more heat for the molecules to get separate. So boiling point will be higher. But when we talk about ethers, in ethers, there is dipole-dipole interactions, and this dipole-dipole interactions are weaker than strong intermolecular hydrogen bonding. Then in hydrocarbons, there are only weak van der Waals forces. So that is why the boiling point of hydrocarbons is least, because you have to give less energy for the molecules to separate out. Okay, so we discussed that in alcohols there is higher boiling point because of intermolecular hydrogen bonding. And we discussed that the boiling point increases with increasing molar mass, because when molar mass increases, your van der Waals force also increases. So when your van der Waals force is increasing, you have to give more heat. So boiling point will also increase. And if the branching in your chain, if there is branching in your compound, then branching decreases boiling point due to reduced surface area. So what will happen? Because when there will be more branching, the surface area will be less. So branching will decrease the boiling point because the surface area is reduced. If the surface area will be reduced, the van der Waals forces will be less. So you have to give less heat. So branching decreases the boiling point. Next is solubility in water. I told you that for alcohols, lower molecular alcohols are completely miscible with water. Okay, and we discussed that they form hydrogen bonds with water molecules. But as your carbon chain increases, and that carbon, that is your alkyl or aryl group, when increases, that is a non-polar part. So when your non-polar part increases, your solubility decreases. Okay. Next, if we talk about phenols, then we said that phenols, they are only sparingly soluble in water. Okay, because the non-polar benzene ring, it reduces water solubility, because the benzene ring to which your hydroxyl group is attached, that benzene ring is non-polar. So if it is non-polar, it will reduce the water solubility. So it can form hydrogen bonds, but it will form less effectively than alcohols. So I hope students, this topic is clear to you now. Thank you for attending the lecture. Have a good day.